hotter than infinity. It sounds impossible, like a contradiction in terms. But in physics, there is a state that is mathematically and physically hotter than any positive temperature. A state so hot that we assign it a number below absolute zero. This is negative absolute temperature. And here is the strangest part. Negative temperatures are not cold. They are not below zero in the way we think. A negative temperature system is so energetic that if you put it next to anything with a positive temperature, heat would flow from the negative to the positive. Scientists have actually created these states in the lab. In 2013 in ultracold gases, and in 2023 in light pulses. They are real. Welcome to Großdenken, everyone. Today, we will explain exactly what negative temperature means, why it is hotter than infinity, and the controversy that still surrounds it. Please support this channel by just subscribing. That would mean a great help. To understand negative temperature, you have to rethink what temperature is. In everyday life, temperature is about average kinetic energy. Hotter means particles move faster. But in physics, temperature is defined by a deeper relationship. It is the change in entropy when you add energy to a system. Most systems have a positive temperature because adding energy always increases disorder. Negative temperature occurs in systems where adding energy actually decreases entropy. This happens when the system has a maximum possible energy, and you have pushed it into a state where most particles occupy high energy states. This is called a population inversion. Imagine a simple system with only two energy levels, low and high. As you heat it up, particles move from the lower to the higher level. At absolute zero, all particles are in the ground state. Maximum order. As you add energy, more particles move to the excited state. Entropy increases, temperature rises. When exactly half the particles are in each state, entropy is maximized. And according to thermodynamics, this corresponds to infinite temperature. But what if you add even more energy? Now more than half the particles are in the high energy state, a population inversion. Adding more energy actually reduces disorder, because you are approaching a state where all particles are in the excited state. Entropy decreases, temperature becomes negative. The temperature scale is not linear from 0 to infinity. It goes from 0 Kelvin, absolute zero, to positive infinity Kelvin, maximum disorder, then from negative infinity Kelvin to 0 Kelvin. A negative temperature is hotter than any positive temperature. So why does water never have a negative temperature? Because most systems, like gases, have no upper bound on energy. Particles can always go faster. The kinetic energy of a gas can be arbitrarily high. For negative temperature to exist, the system must have an upper bound on the energy spectrum, a maximum possible energy. This happens in spin systems, where particles can only be up or down in a magnetic field. There are only two states. Once all spins are flipped, that is the maximum energy. This was first demonstrated in 1951 by Purcell and Pound in nuclear spin systems. Since then, negative temperature states have been created in many systems. In 2013, physicists at the Max Planck Institute in Munich created a negative temperature state in an ultracold gas of atoms. They cooled atoms to near absolute zero, then used lasers to trap them in an optical lattice with a bounded energy spectrum. The atoms achieved a population inversion. The gas had a negative temperature and was hotter than infinity. In 2023, a team led by Ulf Peschel at the University of Jena created a negative temperature state in light pulses. They sent pulses through optical fibers with a periodic modulation that bounded the allowed velocities. When all available states were equally occupied, temperature was infinite. Adding more energy inverted the distribution, creating negative temperature. The system obeyed the laws of thermodynamics. Even nuclear spin systems have achieved these states. In 1994, experiments on silver reached temperatures of 280 picokelvin above absolute zero and 750 picokelvin below. The negative temperature state was proven to be real and not fictitious. Here is where it gets controversial. Some physicists, like Jörn Dunkel and Stefan Hilbert, argue that negative temperatures are not real absolute temperatures at all. They claim the effect arises from using the wrong definition of entropy, Boltzmann entropy instead of Gibbs entropy. The Gibbs entropy never decreases, so it would never produce a negative temperature. Others, like Ulrich Schneider, who led the 2013 experiment, strongly defend negative temperatures. They argue that for systems with bounded energy spectra, negative temperatures are thermodynamically consistent and necessary to describe equilibrium states. A 2024 paper even proposed a new entropy definition that resolves the debate while still allowing negative temperatures. The majority of physicists today accept that negative absolute temperatures are real, but only for systems with a bounded energy spectrum that are properly isolated from their environment. They are not a loophole to reach absolute zero. They are reached by passing through infinity, not by going below zero. So what is negative temperature? It is a state where more particles occupy high-energy states than low-energy states, a population inversion. It is hotter than any positive temperature because heat flows from negative to positive. It requires a bounded energy spectrum, and it has been created in ultracold gases, light pulses, and nuclear spins. It is one of the strangest predictions of thermodynamics, and it is real. Thanks for watching, and hit subscribe for more deep dives into the weirdest parts of physics.